Hello, everybody. So we're going to get into the unit vocabulary for kinetics, lecture video 2. What's the specialized words we need to be able to do for this unit? If you decide to put this off to the end because you think it just means you have to take a little quiz, you're kind of hurting yourself because these words were going to come up all the time. If you don't know what they mean, it's going to make life tough. So first, kinetics. Ooh, yay. Pictogram. Cold's moving slow, hot's moving fast. Kinetics is the rate of the reaction. And this is, or the study of, right? So it's the rate of the reaction. And rate is a big keyword here. I'd like you to underline rate because rate is what's really super important for this unit. Okay? Underline rate. Reaction rate is simply just how much time it takes for the reaction. So how quickly a reaction occurs, time versus reaction progress, till it's done. When it's done, it's going to be done in a certain amount of time. Okay? Collision theory. So here's some molecules moving around, and as they collide, notice they either change direction or they will actually react. Okay, so this is an idea that describes what it takes for a reaction to occur. It starts with the collision of reactants. First, they must come into contact, and then we're going to find there's a few other things that they need to have happen for the reaction to actually take place. And once I know these things, I can affect those things. And if I affect those things, I can essentially affect the rate. Good. So collision theory is a big overarching theory. There's a POGL on it. It's gonna culminate in how do I affect the rates. Okay. An effective collision. So an effective collision example is comes together, they connect, or they collide, has enough energy to break bonds, and away it goes. The reaction happened. If it doesn't have enough energy, it won't happen. So there's one of the things that we need to have for collision theory to work. So an effective collision is a collision of reactants with enough energy in proper orientation to start a chemical reaction. Now, this is where if Monaco and I were here, we would do the handshake thing because, right, if I try to shake hands like this, it's not a good, we don't have a good connection. This isn't a good collision. And you actually need the other right hand. And it's not here. Where are you? Right? And then we have a proper orientation so that the reaction can happen. Okay, then you also need enough energy. If it's too slow, not enough energy, it won't happen. If it's too fast, you might end up just kind of, more of a high five and the actual reaction doesn't happen. Make sense? So two things I need for an effective collision. Catalyst. Notice it says reaction with a catalyst is that dotted line. See how it lowers? What we're going to learn is the activation energy. How much energy do I need to get going? Notice the red line going up and down is smaller. I don't need as much energy to make that reaction go. So a catalyst is a substance that speeds up a chemical reaction, but is not consumed by the chemical reaction. If it was consumed by the chemical reaction, it would actually alter the chemical reaction. This one doesn't do that. It's a special kind of chemical. Not every equation reaction has a catalyst. So this is not always your go-to answer about how I speed up a reaction. Okay, I don't want this to be your default. Okay, certain reactions have catalysts where there's a chemical that will not be consumed by the actual reaction that's going on. Thermodynamics. Okay, this is heat. Okay, the study of entropy and enthalpy in chemical reactions. So entropy is randomness and disorder. Enthalpy is heat. Okay, we're going to put them together. We have thermodynamics. This is a potential energy diagram. You will need to be able to label up 1, 2, 3, 4. You will need to be able to label it up if I move the 1s and 2s and 3s and 4s around. Okay, so you need to know it forwards, you need to know it backwards. This is a graph showing the difference between the potential energies of the reactants and the products. And if they're this way, what does it mean? If it's this way, what does it mean? You're going to get into that. Okay, heat of reaction. This is the difference. Boom, right there between the reactants and the products. And I always do products minus reactants, so I get the right sign. So change in enthalpy of a reaction, the potential energy of the products minus the potential energy of the reactants. This means now that the sign is accurate. Am I endothermic or exothermic? Whew, got it. Enthalpy. Change in enthalpy, we just talked about this, the heat of the reaction. So this is the heat of the reaction, delta H. The potential energy of the products minus the potential energy of the reactants. These are found by looking at the potential energy diagrams or table H. Notice those two have delta H in them. Notice the two definitions are slightly similar. They both have potential energy of products, potential energy of reactants in them. You need to be able to differentiate in the quiz which one goes with which. They're worded very similar because guess what? They mean almost the same thing. Okay, but they're slightly different. So please take note. Highly ordered system versus a highly disordered system. One is a neat, compact thing, and one might look like some of your bedrooms that are all messy, right? This is the measure of disorder in a system or randomness. We could say randomness. Or sometimes we talk about chaos, but they all mean the same thing. The thermodynamics laws favor greater disorder. I have to put energy in to make things ordered. The natural order of things in the universe is lower energy, therefore disorder. Okay? For those of us that are, high school rebels, we're going to like to hear that the universe likes chaos. Forward reaction. This is going from reactants to products. So on your screen, is it this way? Is it this way? It goes from reactants to products, okay? From left to right, forward reaction. Moving from left to right, reactants to products. Reverse reaction is the opposite. That's going the other way. Okay, it's going from right to left, from the products back to the reactants. This is the first time we introduced that a reaction can go both ways, and that's what an equilibrium actually is. And that equilibrium's coming up. We'll get there. Activation energy. How much energy do I need to get up to the top of the hill to get that reaction going? So this is the energy needed to get the reactants to the activated complex. You're going to find that the activated complex is coming up next. That is the point at the top of the hill. Okay, how much energy do I need to get it going? So there's the activated complex. It is a specific point. It is a noun, and it's only that point, and it's at the crest. It's at the top of the hill. That is when the reactants reach maximum energy along the reaction path, beginning the formation of the products. Okay, take a second, write all that down. Okay, equilibrium, huge key piece, right? And this is not the guy on Milks's desk, but a similar thing. Equilibrium, forward reaction, reverse reaction, forward reaction, reverse reaction. This is the state where reactions are happening in both forward and reverse direction at the same time, simultaneously, at the same time, shown in equations with this double-headed arrow. And we're going to figure out that the rate of the forward reaction must be equal to the rate of the reverse reaction. I'm going to say it now. I'm going to say it later. It's rate, 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 never concentration. Okay. Physical equilibrium. Okay, this is like phase equilibrium, physical phase. So the rate of melting equals the rate of freezing. Okay, this is what happened when we were on the flats, when we did the 3 slants and the 2 flats. Physical equilibrium. Okay. Chemical equilibrium. Beautiful. Reactants, products. This is when the reaction rate of the forward reaction equals the rate of the reverse reaction. Reaction equilibrium. It doesn't look like a reaction's happening because every step forward, there's a step back. And it's happening, but it doesn't look like it's happening. Solution equilibrium. So now I have something going into phase. So a solution equilibrium is the rate of dissolving equals the rate of crystallization. For every solid piece that goes into solution, some piece that's already in solution comes back into the solid phase. And within the solution, I create this equilibrium. Okay. Le Chatelier. This is a picture of a tube I do not have. This is a Knox tube, and you change the temperature, and you're going to see that the color changes because that is the chemicals for the reactants and the products have slightly different colors. Okay, that really is it's smog. The reaction equilibrium will shift to regain equilibrium. Now, the piece I missed out on there is because you put a stress on it. So we're going to talk about that in the actual video. It regains equilibrium based on the fact that you stressed it. So it wants to go back to where it should. Okay. An equilibrium stress or shift. This is a change in concentration, heat, or pressure for gases. Okay. Oops, that's kind of messed up. Causing an increase in products or reactants. It switches. So let me push it and then it'll change. Let me heat it up and it'll go one way or the other. But I have to change the equilibrium in some way. That's a stress or a shift. Words, so let's get them mastered. There's a few in there that we need to check to make sure we know how to do them. And you can take your quiz and be on your way. See you.